This last session I want to talk about is troubleshooting. So as we get into troubleshooting and learning what that is, this is going to be one of the core things that you will need to be able to do as an electronics technician out in the workforce. Depending on where it is that you're going, depending on where you're doing, you're going to have to do some sort of troubleshooting. That is part of the job. That's the biggest part of the job. Now, troubleshooting in and of itself is a systematic method to find the problem. Now with that, what we're looking for, SYST, systematic, I think. I don't know. I'm not an English teacher. I think that's right. Systematic method. So as we're going through to solve these problems that come up, we have to then go down to the basics. What do I know? What should happen? How is this going to happen? Things like that. So as we go through this, the troubleshooting and putting it into practicality is just simply applying all the rules that we know to figure out what's going on. So the process that I like to use for this is quite simple. So the process. Step one is determine what is supposed to happen. Determine what is supposed to happen. Now, this can be done several different ways, and I'm kind of leaving this here as kind of a vague descriptor because there's no one specific way to troubleshoot. There's no one specific way to go through and do and be part of this process. But the first step is you got to determine what is supposed to happen. When you come up to a tool, you got to figure out what is going wrong with it. What is it not doing? What is it doing that it's not supposed to? Things like that. So you're going to rely on a couple of different things. One, you could rely on the last operator that was using the equipment. They should have a log somewhere of why it's down, or asking them what was going on. Also, just trying to figure out, if it's just a basic circuit and not a actual tool set or things like that. If you're working on your circuit, you just got to figure out what is supposed to be happening. Now, the way that we determine that, especially in the basics, is do the calculations. Find out exactly what is supposed to happening based on the information you're given. You can also go through and you can take into account some of the other tricks and tools that we've learned, doing some quick calculations. What should my voltage drops be? What are they actually measuring? Do I have anything that looks funky? Is there something that just inherently my gut says, this is wrong, it shouldn't be this way, or those numbers don't quite add up to what they should be, or things like that. So you will learn and you will develop a bit of a gut as you get going as far as what could be wrong with this and kind of a direction to go. Sometimes, based on the evidence that we find, we have to disregard our gut because maybe we're thinking the problem's here, but all the evidence is showing it elsewhere. So it's kind of an internal struggle, and there's no one set way to do that. But the biggest thing you have to do is be able to think about it and literally go through and determine what is supposed to happen with that. Okay? So the other steps that we do is determine what is supposed to happen. Build and test the circuit operation, or build and test the machine to find out what it is that it's doing. This is what it was reported to be doing. Is it still doing that? Can we duplicate the fault? Is it a consistent fault? Is it an intermediate fault? Now, when we get going through and studying with these, the intermediate faults are going to be the worst sucky things that we have to work on because they only happen at certain frequencies. They only happen certain times. They may only happen when the tool is first booting up or when it gets close to the end of the day. Things like that, we have to kind of build all of the information together. This is also why documentation is such a big thing and why it is so important. Is as you document what you saw, what you've seen occurred, you can put that in there and then people can reference it back saying, hey, this is when this problem was noticed. It happened here, 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 and here. Okay, now we got some dates and times. Maybe we can correlate it to something else. Sometimes it's as simple as they were running another piece of equipment at the same time and there was some interference that got created. Hey, at least now we know the source. Now we can start tackling the solution for this, which that can sometimes be a problem too. But just trying to diagnose where the problem is sometimes is the first battle that we have to overcome. And then based on our measurements, based on our observations, we got to see what happens, what to go on. And then go in, once we've identified a problem, we correct it. We swap a part out. We move a component. We isolate what is going on until we can get to the point where it works correctly. And then we correct it. Then we correct it, we verify it's running, and we put it back in there. And all of our measurements and all of our things should be back within, our margin of error that is predetermined. And in our program, it's going to be 5%. All right. So kind of the steps that we had. So number one was determine what was supposed to happen. Number two, we're supposed to build/test the problems to get verification. So we're going to build and test for verification and repeatability. Now there will be some instances that these faults are the operator's error, which does happen. And in that case, we just have to correct the error. We have to make sure that they know don't do that again and kind of move on. When we are building our circuits for the first time, a lot of time we're going to be building this test for verification. That's part of where we determined there was a fault. We built the circuit we were going to test and it's not working. Why is it not working? Again, a lot of times it could be operator error. Okay? So then we build and test, and then based on measurements and observations, we determine what is wrong. And I'm going to put what is wrong in quotes here because sometimes what we're looking at isn't the right part. And so then we have to reevaluate. So based on measurements and observations, determine what is wrong. Then 4, we have to make a correction of some kind, whether that be replacing the part, replacing wires, moving wires to the correct positions, whatever it is, we're going to have some sort of a correction. And then on our last step is we have to verify proper operation. After we made the fix. And sometimes we will go back. We'll come through, we'll make a correction, and then we're going to verify, and then it still doesn't work. Okay, so then we got to come back up here. We already have this built. What do we need to do? How do we repeatability? Can we change? What can we do? We don't want to just be throwing parts at it, because as we just throw parts at it, that's going to cost our customers money, especially if it's ones that we can't reuse. If we're trying to determine on a circuit, we have to isolate the different components, make sure everything's working correctly, making sure everything is measuring to where it's supposed to be. We could have put in a 1K resistor when we meant to put in a 1 mega ohm resistor. So that could be causing problems. Or vice versa. We thought we were putting in a 1K and we plugged in a 1 mega. It could be any of those things. So we just have to go back and verify our parts, verify the test conditions, all that kind of stuff, and we just go through this cycle. All right, so in our specific circuits that we're going to look at is troubleshooting a series circuit. So we're going to start off with a very, very basic system. And we'll get my pen back up. So what we'll have is our DC power supply is going to come around. We're going to connect into one resistor here, and one resistor here. So I've got my voltage source coming in. I've got R1 sitting here. I've got R2 sitting here. And I've got R3 sitting here. All right, R1 is listed in the schematic as 100 ohms. R2 is listed as 330 ohms. And R3 is listed at 450 ohms. And we have a 10 volt signal applied to all of this. So a lot of times what we're going to be looking at first is I have to verify a few things. So if my circuit's coming up and I have values that are not matching up, I have to make sure, one, it's connected up right, okay? So the first thing I'm going to do is make sure that I have got the connections displayed in my schematic on my breadboard. Does my source, my voltage total, connect in and only into R1 on the positive side? Then does the other side of R1 connect to only R2? Does it connect R2 only connect into R3? Does R3 only connect back into the negative of my source? We've got to make sure that that's happening. Okay, so that's kind of step number one, is verify our connections. Make sure that on our breadboard we have connectivity between our positive point to the one side of R1 and check all those connections. Second thing is we want to verify, did I put the right components in? Okay, if I'm like, okay, I did put this in correctly, and I've got continuity, I got things checking out to where I have connection points, basically. Okay, did I use the right resistors? Did I use 1,000 ohm? Did I use 100 ohm? Did I put a 10? Did I put a 1 in when I should have put 100 in? You know, whatever it is, we just got to kind of check and verify. And then we kind of go through the process. Then check my source. Do I have 10 volts coming into this thing? Is my power supply turned on? Sometimes the power supplies we have in the lab have an extra knob to enable the output, or an extra button to enable the output once we've set everything up. Did we hit that button? Do we have a good connection? Are our connectors loose? You know, so we have to kind of systematically go through these things. So the other thing we're going to do is, based on this circuit, we're going to kind of determine, we're going to have a series of faults or different circuit opportunities. And this kind of is giving you an inside look into what I deal with every single day as an instructor. And this is just a good example of, okay, I have a list of things and a list of circuits. Here's what they're getting. They're all different. I got to figure out what's going on with them. But it's also, these are different types of situations you could see and have occur when you're actually in the workforce. So what I'm going to look at is I have 3 different circuits. So I've got a component listing. So a component coming down, and I have circuit 1, circuit 1, circuit 2. That's not a 2. Circuit 2 and circuit 3. All right. So I've got my outputs. Now on this, we have to go with the information that we're given and not necessarily making any assumptions as far as what values are going to be. So we're just going to go strictly based off of what I am actually measuring. So my components is I'm looking at the voltage of R1, the voltage of R2, and the voltage of R3. So basically what I did here is I took my DMM in voltage mode and I connected it to every single one of these and measured the voltage across each component. So then I moved my meter over across R2, moved my meter across R3. So these are my 3 data points that I have to check with: the voltage of R1, voltage of R2, voltage of R3. So then I come back over and look at my values. So in circuit 1, I'm getting 0 volts across R1. I'm getting 4.231 volts across R2, and I'm getting 5.769 volts across R3. Now my next circuit, now remember these are completely independent of each other, so just because circuit 1 has something going on doesn't mean circuit 2 is going to follow. They're completely independent options. This is just going to give you some examples of what to look for. Circuit 1, I have 1.136 volts on R1. I have 3.750 volts across R2, and I have 5.114 volts across 3. And then circuit 3, I've got 0 volts across 1, I've got 0 volts across 2, and I have 10 volts across 3. All right, so now that I have my options, now I have to kind of determine what are my potential failure modes in this circuit. What do I have that I can use? Well, the first things that we have is we have to find out maybe somewhere I have an open or I have a short. These are going to be my 2 major values. The other one I might have is I may have a wrong value. Okay? But when I'm doing this, we can kind of assume that this one is going to be few and far between because we've already done our verification that the components are what they say they are. We pulled the 100 ohm, we isolated it, we measured the resistance, it's good. R2, we isolated it, measured the resistance, it's good. R3, we isolated it, measured the resistance, and it's good as well. So a lot of times this one is going to get taken care of as an option while we're diagnosing the circuit, while we're doing our step of gathering information. our verification steps, things like that. Okay, so now we have to figure out, so if that's not an option, then I've got a few things that can happen. I can have R1 can be open, R1 can be short, R2 could be open, R2 could also be shorted. I've got R3 is open, and R3 again could be shorted. Now we could have other combinations. We could have R1 and R2 is shorted. R1 and R3 is shorted. R1 and R3 is open. It kind of depends on that. But right now we're going to go through and assume that there is only one failure at a time. Now, a lot of times that's usually the case, but there can be some where we could have multiple components because one of them took another one out. So, if something shorted out and then we burned it up, it could burn up another component. It just depends. Generally, that usually is a cascading failure, and when we make a repair, then we'll see this thing pop back up again, and then that's gathering the information, gathering the notes, that kind of stuff. All right. So now we have kind of the idea of, I verified that my values at least are correct. I verified that I have my 10 volts. And then I have to go through and figure out, based on my individual circuitry, what my data is telling me is my next place to look. So the next step, so one is we're going to look at our data. And our first step, that when we look at this, that there's probably a problem with circuit 1. There's probably a problem with circuit 3 because, for one, we got a bunch of zeros in there, where if we've designed a circuit, we may or may not want this 0 volts, depending on what our application is. Now, when we're dealing with just a series circuit with resistors, zeros are bad news. If we have a 0 someplace, that means something is not doing its job with the components that we've learned. Okay, so I know for sure I probably have a problem with circuit 1 and I probably have a problem with circuit 3. I just got to figure that out. Circuit 2, well, there's values in everything, and maybe it's right, maybe it's not. We have to kind of determine that. In looking at it originally, we're just kind of glancing with what we know. We know that according to Ohm's law, that the larger resistance values we have are going to have a larger voltage drop. So if we look under our values, R3 has the biggest resistance. So therefore, R3 should have the biggest the biggest voltage drop on all of them. And if we look at our data, that trend still holds. So we know right off the bat that at least R3 is bigger than the other ones. The data is correlating that. And again, it's just giving us some validation that we understand what's going on. We can see these patterns as they start to erupt, or start to emerge, not erupt. And we kind of go from there. All right, so then we got to look at some of our values. So number one is we look at the data and we kind of see. We know that there's, like I said, there's probably something wrong with circuit 1. We know there's something wrong with circuit 2. We have built our set of potential failures. What could happen? And then our third step is we're going to look for the easy things. Now, the easy things are going to be places where I have 0 voltage drops. When I know I should have some voltage and I'm getting 0 voltage drops, there's probably a problem with that component or somewhere nearby. Another one that we're going to look at is 0 current flows. So later on, current is going to be a bigger factor when we're looking at parallel circuits than with series circuits. Series circuits, our primary indication is going to be voltage drops. Okay? Then I'm going to look at my total voltages. I'm going to make sure that Kirchhoff's voltage law is still in effect, that I'm taking everything into account. Because there's sometimes we may look at these and there may be something else causing it that's unrelated to this part of the circuit. So it could be something later on, it could be something previous. So another red flag that we want to look at is we have our 0 voltage drops, We have our total voltages. We want to look for some wildly outrageous values. Okay, that's another indicator of where we want to look. If something is just absolutely off compared to everything, that's kind of a spot. And then thinking about the patterns that you do know and that you go out and that you can kind of come up with. Again, this is assuming you have some experience with this. If you don't know what they should be, you're not going to have anything to reference it by, and that's okay. We got to start somewhere. So nothing else, look for the easy things. Our 0-volt drops, 0-amp current flows. Look at our total voltages, make sure that Kirchhoff is being applied and we're not forgetting something, and looking for wildly outrageous values. Okay? So in this hierarchy, or not the hierarchy, this list of things to look for, we know that on circuit 1, we have a 0-volt drop. That's going to cause me to be suspicious because it should have some voltage based on these values. Looking at circuit 3, I've got multiple zeros, but I've also got a 10, which is a wildly outrageous value because we're only putting 10 volts into the circuit, and most of the time we're not going to design this circuit to have one component take all the voltage when there's multiple things put into place. So that kind of is another red flag, that maybe that this guy is a wildly outrageous value. 0 volts is very, very conceivable, but having something take 10 volts, that kind of raises some red flags to me. All right, so with that being said, we're going to continue to look on these. And we kind of apply all these principles, and then we just start digging into it. We just start picking a point and figuring, okay, where is my most likely, the most probable, maybe even the easiest fix to start with, okay? So we kind of go into our rules. So when we go in and we look, we know that current should be the same everywhere in a series circuit. So if I have current meters in here and I'm getting different current meters or current readings in different parts of the circuit, that means I've got something going on. I've got maybe something that's coming in with a parallel network, and I know we haven't learned about that yet, but we will in the next week. But it's just something to be aware of. Okay, so based on our voltage circuits up here, we're going to kind of go apart these one at a time. So we're going to look for the easy things. So our 0-volt drops. Now this one has 2 0-volt drops and a wildly outrageous value. So there's kind of 3 things going on with this one. Circuit 1 only has one potential red flag right off the bat, which is a 0-volt reading. So then what we got to do is figure out, okay, let's start with circuit 1. Let's go from there. Okay, so I'm going to scroll down a little bit here, and we'll bring that information down. So circuit 1. And I will redraw the circuit that we have to work with so we can kind of play with it and mark it up and do what we need to do with it. I got 10 volts. I've got R1 sitting at 100 ohms. I've got R2 sitting at 330 ohms. And I've got R3 sitting at 450 ohms. Okay, so on here I know R1 was reading 0 volts. R2 was reading 4.231 volts, and R3 was reading 5.769 volts. Okay, so again, just starting with what we know. We know that in a circuit, my Kirchhoff's voltage loop has to be, my 10 volts in has to equal 10 volt drop across everything. So if we look at it and I do my loop, I've got 10 volts on one side, and then that's going to be equal to a 0 volt plus a 4.231 volt plus a 5.769 volt. If I add those together, I get 10 volts is equal to 10 volts. So I know that according to Kirchhoff, everything checks out. So at least I know that I'm not losing that 10 volts somewhere else. It is all accounted for in this circuit. So that is actually really good. So then I kind of start to going in there. Okay, if I have 0 volts, what does that tell me? If I have a component that equals 0 volts, that means what? Okay, I have 0 current, oops, not volts. is I have zero current running through that component. So therefore, if I'm looking at R1, that means none of my current that's coming out of my positive, it's hitting this junction at R1. Something is then making that current go out and around and completely bypass R1. So if I have voltage across everything else and I have no voltage across one component, that simply can mean there's no current. So how do I get a component to basically have a bypass to where no current goes through it? Well, the easiest answer is R1 is shorted. Because a wire has approximately 0 ohms of resistance, and electronics is lazy, electricity is lazy, so that current is going to flow through that wire instead of trying to push through the 100 ohms. It's just going to look like a big wall. It's going to go around it and take that path. So if we come across where a component value is 0, that means R1 is most likely going to be shorted by some other component. We either had a piece of wire fall onto our circuit, or in the most common occurrence, what happens is on our breadboard, so our breadboard looks like this, so there's 5, and then there's the holes that sits in it. And then we have whatever other rows that we're doing. Most likely what happened is we took our resistor, plugged it in from this hole, ran it in, and plugged it into this hole. Now what do we remember about the breadboards? Every group of 5 of these is connected together. So there's literally a piece of wire running between all these points, which then actually goes to support our theory that R1 is shorted, because if all these lines are together, that means that current went down through this piece of metal and then back up on the outside and completely bypassed that resistor. So what we need to do is we need to move one of these legs into the adjacent line. So the correction would be to unshort R1. So then what I will have is my, let's see, 1, 2, 3, 4, 5. So this is like row 6, 7, 8, and 9 on my breadboard. Then I have that gap, and 1, 2, 3, 4, 5, 1, 2, 3, 4. So then all I need to do is then take my resistor, come out of this connection, and move it over across that line, because we know that this breaks whatever connection there is. So generally, a 0 voltage signal on a component, on a single component, is going to mean that that component is shorted somehow. Now, we can also check to measure that using our resistance meter or a continuity meter, but then that requires us taking apart the circuit and finding out, in the circuit, how does it measure up? Do I just disconnect the component, measure it, go from there, things like that? We can actually get those measurements where we'd see a 0 ohm resistance. But generally, in a series circuit, if you have one component that's not reading any voltage at all, that should be, generally that component is shorted. And generally, when you're in the lab working on it, you've done something like this. Most of the time, this is the culprit for having that component faulted out, especially in the lab. Now, in industry, it could be the same thing, or it could just be that something fell and shorted out these wires. We had, a machine that was cutting wire or things like that, and a piece got thrown errant, and it landed on top of the circuit board and shorted out that resistor. That's one thing that we could see to have happened. Now, when it shorts out, it doesn't necessarily mean that it has burned up or that there's something wrong with the component itself. Usually that means it's either plugged in wrong, incorrectly, or that the component itself has something external happening to it. And that's not to say that just because this guy gets shorted out, it could cause issues down the road. If that resistor was needed to maintain current levels and all of a sudden we lose that resistance, current is going to increase, which means there's going to be more power. And another component later on down the road could actually fail because of that increase in current. So just keep that in mind, that it could be a cascading issue like this. This one got shorted, therefore something else got too much current, therefore it got too much power, and therefore that component burned up. But just a 0 voltage reading across that component with nothing else is usually an indication that that component is shorted. That's going to be one of the majority rules that you can kind of count on. It's not going to happen all the time or every single time, but the vast majority of the time, it will indicate that R1 has been shorted. Okay, so we've taken care of at least the easy stuff, at least the very first easy step. Because circuit 2 has some values, circuit 3 has got 2 of them that are reading 0, and we only have the option that one of them is shorted. Most of the time, we're not going to have R1 and R2 are shorted. That could be an answer. And with our information, there's no other way that we could suggest that. Or to arrive at that conclusion, we'd have to put multiple problems down saying it could be this or it could be this. And then at that point, then we're at least eliminated everything else down to 2 possibilities, and then we got to dig in and do some more work to correct the problem at that point. So it just kind of depends on where we're going. All right, so now at least I've got circuit 1 figured out. I am very confident that R1 is shorted because it's exhibiting those signs. We have no voltage, no current. We can prove that it's working. And then when we go and look at it, oh, lo and behold, this circuit had those pieces completely shifted. They were all on the same row, meaning internally it shorted itself out, and we needed to translate it into something that looks like this and jump the gap, redo our circuit. Now it's going to work fine. All right, so we've got circuit 1 taken care of. So now what we need to do is just kind of do what our other steps were. We got rid of the easy steps, okay? The other ones are kind of hard because we have multiple things that could happen to them still. So we want to be able to look at what should my circuit be. Let's just take this for an example and let's actually look at it. What should my circuit actually be doing? So I'm going to jump this down into a different color. So we're going to look at what is normal. Because now I need to compare my normal to anything going on. And I could have even done it to this one too, but like I said, with one component reading 0, it's pretty easy to determine what's wrong with it. So what is normal? Okay, so if I go through and look, I know that in my list, I have one circuit 2 has values across each of the resistors, and then circuit 3's got zeros for resistor 1 and 2 and a 10 for 3. So what is normal? So voltage of R1, we can just pick a value. We need to solve what would be the normal voltage across R1. The easiest way to do that is just use voltage divider because it is a series circuit and we're looking for the voltage. So the voltage of R1 is going to be R1's value over my R total in series times the voltage applied. Okay, and in this case, the 10 volts is being applied to this whole circuit. So I'm going to get 100 ohms divided by, I've got 100 plus 450, that gives me 550. 550 plus 330 is going to give me 880. So I'm looking at just at R1, 100 ohms over the 880, and I have my 10 volts applied. So when I run through that calculation, what I'm going to get is the voltage of R1 should be 1.136 volts. Well, if we go back and look, my circuit 2 value, I have 1.136 volts right there. So that's a pretty good indication that if I got exactly what that thing is measuring, that hey, I might be looking at a situation where this could be my normal. Meaning it's working correctly and everything is going the way I have. And there is not actually a problem on circuit 2, which is also what we have to look at when we're working with these types of circuits. It's what I have to look at. I have a list of what it should be, and then any deviations from there, we got to troubleshoot it. So we're looking that maybe this one is our normal value. But to verify it, we just need to at least get one more value, and in the process, we'll get the other. But we want to have several data points that indicate that this thing is working correctly. All right, so if we come back down into here, and I got to scroll back down so I have room. So we're going to check one other value using the same method. So we'll come in and let's look at the voltage of R3, because that's going to be the biggest one. So that's going to be R3 over the resistance total in series times my V applied, or my VN. So R3 was my 450 ohm resistor over the 880 ohms, and I put my 10 volts of applied to that. So then when I go through and calculate that guy, I've got 5.114 volts. So there we go. And then if I go back and look, my R3, 5.114 volts. So now I have 2 out of those 3 that are verified with my calculations that those 2 are correct. Okay, and the last step is I can go through and calculate this value, this 3.75, to see if that's what matches across R2. But I also have the ability to just use Kirchhoff's law. So Kirchhoff's voltage law, as we remember, says that the voltage drop of R1 plus the voltage drop of R2 plus the voltage drop of R3 must equal Vn. So I can do 1.136 volts plus my VR2, which I haven't calculated yet, plus my VR3, which is 5.114 volts. All of that has to equal 10 volts. So if I run this through my calculations and solve for my unknown, my VR2, I'm going to find out that VR2 is equal to 3.750 volts, which is what I was given up in the top one. So therefore, my normal operation is one of my circuit conditions, and so therefore, on circuit 2, this is normal operation, no faults. Now, we may not always have that option, and that may not always be the case, but it doesn't hurt to check. Make sure that we are at least operating under the assumption that this thing is correct. So because these values match, circuit 2 is operating at normal operation. No faults, nothing detected, nothing weird, nothing hinky. And so then if we come back up to this list, we have determined that up here, we had R1 was shorted. We know that one for sure. And then we know that this went from normal question mark to normal, because everything matches up to what calculated it should be. All right, so now comes our big circuit. So circuit 3 is going to be our most difficult looking at this, because again, we've got to figure out what's going on with these values. What are we looking at? How can this thing have any problems? So again, we go back to our rules. Okay, we'll bring this down and let's redraw our circuit again. Okay, so come up here. We've got our circuit. We've got R1, R2, R3. R1 at 100, R2 at 330, and R3 at 450, and my voltage in is 10 volts. All right, so we know that based on those values, what we had, R1 was reading 0 volts. R2 was also reading 0 volts, but R3 was reading 10 volts. Okay, so as we get going and we look into this, what can cause 0 volts across a component? Well, the easy answer is 0 voltage equals 0 current. So there is no current flowing from R1 to R2, but R3 has current flowing through it, so that means there's a couple possibilities. We could have a short that goes like this, and we could have R1 and R2 shorted. That is a possibility, and it's a 100% valid possibility. And with these options, I can look at it and go, does the data support? And the answer is inconclusive. Because we have no current data. So according to our data, we can say that R1 and R2 shorted is a possibility because there's nothing to say otherwise. If we were measuring current from R1 to R2, we could see that there would be current flowing. We could also see what the total current would be flowing, that kind of stuff as well. So we have to kind of take that into place. So there's inconclusive, like this is a possibility, but there's no way to actually say if this is the answer. Generally, again, when we're looking at these, in a series circuit, most of the time we're not even going to have the option of R1 and R2 shorted. We're going to be looking at a series or at a singular failure, not multiples. Not to say that it couldn't happen, but without more data, we can't conclusively prove that R1 or R2 is shorted. Okay, so that is a strong possibility, and even based on the information we have on hand. Okay, the other thing we need to look at is, okay, so if that's the case, and we have no current flowing through this, what other options do we have? Well, we know if R1 by itself was just shorted, then we'd have 0 volts, okay? But then that only accounts for R1. If R2 was just shorted, then that's going to account for the 0 volts, but not for the 0 volts from R1. So individually, we've got R1 and R2 shorted that we can't use because the data doesn't just support that condition. I also have the option of R3 shorted. I also have the option of R1, R2, or R3 are open. Okay, so if R3 was shorted, we would have 0 volts across R3. We don't. We have 10 volts. So right off the bat, that one has to go away because of 0 volts is 0 current. We have current. We have voltage throwing through that component. Okay, so the other option is, let's look at this. So if R1 was open, so that means we came in here and we disconnected R1. We made this circuit do this. I'm going to draw these in individually so I can erase them. Okay, so if we say R1 is open, so that means we've lost that component. Where's my current path? Well, the current's going to come out of my positive, hit this open, and have nowhere to go. Current coming out of my negative is going to come around, go through R3, R2, but then there's no place for it to go. So with R1 open, there is no current path in the entire circuit. There's nothing. So if there's no current in the entire circuit, that means R1 gets no voltage, R2 gets no voltage, and R3 gets no voltage, which means none of the data points that we have match that conclusion. If R1 is open, nothing has voltage. If R2 is open, so same thing. We come back in, we plug our R1 back into the circuit. If we take out R2, again, no current flow for any component, so there's no way that any of these components could have that value. Okay, so that means R2 cannot be open based on the data we have. Last but not least, what if we take R3 out? Well, again, it's the same situation. No current path means no voltages. So now we have to take into account, well, R3 is no longer open. Well, that just knocked out all of our possibilities. What do we do now? Well, one of the things we also have to take into consideration is how are we getting this data? So if we come back and look at R1, we're going to come in, we're going to assume that R1 is opened. I'm then going to come in with my DMM on voltage, and I'm going to measure across this. Well, what did we just find out in the last example we did when we were solving for the voltmeter? We found out that that voltmeter has some resistance to it, no matter what meter we're using. So therefore, when we make this connection, if there's no connection point here, we plug that meter in, and all of a sudden, all the current is then going to go through this meter and back out, which means we just made a complete circuit. So now that there's current flow through everything. So if I go in here and measure this guy, one of the things that we didn't quite cover and that we need to talk about as well is our voltmeter does have a resistance. And the resistance that the voltmeter has, so our voltmeter, it has a very, very large resistance. And the reason for that, and we will talk about this more when we get into the parallel circuits, is because when we go to measure things, we are measuring things in parallel, normally. And what happens with this is when we add this extra part to the circuit, we've now added a separate current path that can flow that direction as well as flow this way through the resistor. And we want this bleeder current, so I bleeder, or I meter, however we want to look at it, I want this bleed current to be as small as possible so I'm not affecting my whole circuit. So I have to have a very, very large resistance to create a very, very small current going through this meter. Also, when I put things in parallel like this, when I give it options for current to pass through, that my total resistance in these two components is now going to change, and it's going to be smaller than my smallest value. So just kind of plug that into the back of your brain that right now, that in a parallel situation, my total resistance for that branch, for that parallel network, is going to be smaller than whatever my smallest value is. So if I have my V meter with a very large resistance compared to the 100 ohms, that very large resistance isn't going to change this much, and maybe this thing will drop to like 99.8 ohms instead of 100. This is also a phenomenon that we're going to see that's called that's called our loading effects. So when we actually go to measure circuitry, our meters actually impact the circuit. So voltmeters we want to be very, very large because of how we use them in parallel. And because we want a very, very tiny amount of current to be siphoned away from the main line so we're not affecting the circuit. Okay, so typically the voltmeter has a very, very large resistance. And in this case, we're looking at greater than or equal to 10 mega ohms. That's ideally what we want these meters to be. So 10 meg against the 100 ohm is going to give us something very, very similar to 100, if not 100 when we go and round it. So it's not going to have a very much of an effect on it. Okay, with that being said, with understanding that because this meter has resistance, we now created a closed loop. We created a circuit or a current path. So now when we go to measure this, I've got a 10 mega ohm resistor now is connected from here. This R1 we'd said had gone away because we're assuming it was open. Now I plug my meter into that position to measure it. The current is then going to have a path, and I go through the 10 meg, through this teeny tiny 330, through this teeny tiny 450, and back to the 10. So again, using voltage divider rule, the voltage of R1 when it is open, essentially I get the resistance of my meter over my R total in series times the voltage applied. So V in. So my meter is 10K. My total series is a 10 meg, sorry, this should be a 10 meg, not 10K. 10 meg. I have 10 meg plus 330 plus 450. So that's going to give me 10 meg, or 10.000760 mega ohms. So those two teeny tiny resistors, 2 and 3, are basically going to be looking at being rounded out even if we plug this in. So even if we plug this value in, we'll go 10 meg divided by my 10.00076 times my 10 volts. This would give me 9.999 volts. So in all sense, with R1 being opened, then I plug my meter into the circuit, all of a sudden, I would get 10 volts across R1. But I'm not getting 10 volts across R1. I'm getting 10 volts only across R3. So what happens in this situation is when we get to a series circuit, when one component is dropping the majority, if not all, like the vast majority, not just the simple majority, pretty much all or every little bit of voltage or 98% of the voltage or things like that, that component is going to indicate that there's an open, just based on how the voltmeters work. So our data set says that I have R3 listed here as 10 volts. So that means if I was to go back and plug this back, if R1's still sitting there and R3 is gone, and I have my voltmeter sitting here, that means now I've got this 10 meg put into place of R3, and so this effect up here is now shifted down to R3, and R3 is going to be seeing 10 volts versus any other component. So when we have multiple 0 volt ranges or 0 volt readings on a series circuit, and we have max voltage on one component, most likely that component is open. And our meter, is measuring the drop across itself. This is loading, our loading effect. So we put our circuit and we put our meter into a position where now instead of measuring the component, it became the component, and the DMM actually then measures the voltage drop across itself. So one thing to be aware of, our meters will affect it. And then in the end, the final answer comes down to where R3 is our culprit, R3 is open, and it's because our meter actually completes the circuit that we get that weird reading of it dropping everything. And that's the reason in the physics of why we get that. So anytime we measure an open, we should get the entire voltage drop in series that's available to it. Okay, so if I come back up. So my first circuit was we determined that R1 was shorted because only it had 0 volts across it, meaning 0 current flow, meaning the current was being bypassed away from that component. Circuit 2, based on our calculations of running through this is our normal operation. There is no failure in that. And then we get to circuit 3, which is going to be determined as R3 is open, due to the fact that every other component is not reading anything, but R3 is reading all the voltage in series, meaning the meter has taken charge of that and is now messing with the circuit. But it is also showing where that fault is because of that. So as we go through with these troubleshooting things, like I said, look for the easy solutions. This now all of a sudden becomes an easy solution, even though I have multiple components not reading anything, when one of them is reading everything. So in that instance, that becomes an easy situation to determine, hey, there's only one component getting all the voltage. That component is probably open due to its configuration in series, because when we went to measure it, my meter created that connection point, and now all the voltage is being dropped across that meter itself. So I've got an easy solution for shorts. That component by itself isn't going to read anything, and then opens everything but that component is not going to read anything. And then my normal one is thrown in there just to give us a baseline. Now, we could have gone through this differently as well. We could have solved, R2 and just said, hey, let's compare, what we did. We could have solved the whole circuit right off the back and said, okay, what voltages do I have based on what I'm given? And that would have quickly determined that normal was circuit 2. And then we would have definitely seen that say, hey, wait a minute, R1 is definitely a problem. Circuit 1 definitely has a problem because there's no voltage across R1. Well, how do I get the voltage not across R1? I don't have any resistance there. And the only way to get rid of a resistance is to short it. So if we also remember our failure modes, a short is a sudden decrease in resistance. Most likely going to 0 ohms. And an open is a sudden increase in resistance, mostly going to an infinite number of ohms. Okay, now in this situation too, even with R3, it opened up, which means between that point to that point was now a near infinite amount of resistance. If we measure it with our DMM, with everything else turned off, at that point, just everything else connected, R2 disconnected, the voltage connected out of it, and we're just measuring the connection points, our meters would read OL, because air itself has a very, very high resistance as well, and so we've got that air gap. That's another phrase that you hear, an instantaneous air gap. Means we had something that was supposed to be there and is no longer there. Either it got removed, never got connected, or it burned up. And it burned up the component, so now there's nothing between those leads, and now we have this open, and when we go to probe our voltages, the DMM actually comes in, and it has a smaller resistance than infinity, but a large enough resistance that normally it's not going to affect the circuit, that now we could be like, okay, putting that into place, we're going to put this astronomically huge measurable value, and we see our circuit follow that trend. We put huge resistance in the circuit, that voltage is then going to drop across that resistance. Just basic Ohm's law. As the resistance increases, the voltage drop also increases. So we slap in a value that's bigger than 100 times than these guys, that voltage drop is going to go up 100 times of that component. So one way that we're going to use all of our skills. So in this process, we understood, we saw what a short does, we saw an open do, we saw the actual definitions of these. A sudden decrease in resistance going to 0, a sudden increase going to near infinity. 10 meg compared to 330 is in an infinite resistance, basically. It's so much bigger, it's going to appear as an open. We also learned how to verify using Ohm's law, okay? The relationships of Ohm's law, not specifically, voltage is equal to current times resistance, but the relationships of how these work. We saw what happens when we have no current flow going through a component, no voltage drop. When we have no current flow across the whole thing until we measure it, then we create problems. So we're able to see all these different applications. We also used Kirchhoff's voltage law. So everything that we've learned, we're going to apply in our troubleshooting techniques and our troubleshooting procedures. Now, there's way too many steps to try to calculate and try to prepare a process flow for every eventuality and every single thing that could happen. But as long as we go back to the basics, we can work through it. And we can determine, hey, is this supposed to happen? Is this right? Is this wrong? What are my options? And then we can go back to figure out, hey, this board is bad. If I don't have a full understanding of how a circuit board is working, I have a tool that has multiple circuits on it. All of a sudden, I start slapping in meters and things like that. I can start eliminating. Well, I know if I put 5 volts into this board, I should get 25 out of this board. I got 5 coming in, 25 coming out. Okay, that board's good. Well, then that 25 volts gets fed into this board and then gets split up. Oh, wait a minute. I'm not getting the split like I should in other areas. So my problem's probably in that board. That is where this troubleshooting comes into it. So we just got to take a systematic approach into determining what do I know, what can I trace, what should be happening versus what is happening. And this is the process that you're going to learn. It's going to take a long time to get down to be really good at this. But in the end, it will be worth it.